Welcome back to Let's Talk About Data. This week, we're diving into model selection and tuning, two of the most important steps in creating a successful machine learning model. In this episode, you'll learn how to choose the right model for your problem, techniques for hyperparameter tuning to optimize performance, cross-validation and evaluation methods to ensure your model generalizes well. If you're excited to master model selection and tuning, don't forget to like, share, and subscribe. Let's get started. Model selection is the process of choosing the most appropriate machine learning algorithm for your problem based on the dataset and the task at hand. Factors to consider when selecting a model: data type, categorical, numerical, time series, etc., size of the dataset, problem type, classification, regression, clustering. Common models and their use cases. Linear regression, used for predicting continuous values, for example, house prices. Logistic regression, used for binary classification, for example, spam versus not spam. Decision trees and random forests, used for both classification and regression with nonlinear relationships. Support vector machines, SVM, used for classification tasks, especially in high-dimensional spaces. Hyperparameters are parameters that are not learned from the data but are set before training. Examples include the number of trees in a random forest, the learning rate in gradient descent, or the depth of a decision tree. Techniques for hyperparameter tuning. Grid search exhaustively searches through a specified set of hyperparameters. Random search samples hyperparameters randomly and can be more efficient. Bayesian optimization, a probabilistic model-based method for finding optimal hyperparameters. What is cross-validation? Cross-validation is the technique used to assess how well a machine learning model generalizes to unseen data. K-fold cross-validation splits the data into K parts. The model is trained K times, each time using K-1 parts of the data and testing on the remaining part. Evaluation metrics: accuracy, proportion of correctly predicted instances, precision, recall, and F1 score, important for imbalanced datasets. Mean squared error, MSE, for regression tasks. Tuning a random forest model using grid search and cross-validation. Importing necessary libraries. Random forest classifier. This is a machine learning model used for classification tasks. It's part of the ensemble module in Scikit-learn, which combines multiple decision trees to make predictions. Grid search CV. This is used for hyperparameter tuning. It performs an exhaustive search over a specified parameter grid and finds the best combination of hyperparameters based on cross-validation. Load under iris. This loads the iris dataset, which is a simple and well-known dataset used for classification tasks. Loading the data. Load under iris. Loads the iris dataset, which contains features, data.data, and the target labels, data.target. Uppercase X, the feature matrix containing the input variables, sepal length, sepal width, petal length, and petal width. Lowercase y, the target variable, which contains the classes, species of iris. Defining the model and hyperparameters. Model. We create an instance of random forest classifier, which is the model we want to train. Param_grid. This dictionary defines the hyperparameters that we want to tune. And estimators, the number of trees in the forest. We are testing two values, 100 and 200. Max under depth, the maximum depth of the trees. We are testing two values, 10 and 20. Performing grid search. Grid search CV. This performs the grid search with cross-validation. Estimator equals model, specifies the model to be used for training. Random forest classifier. Param under grid equals param under grid, specifies the grid of hyperparameters to search over. CV equals 5. This means 5-fold cross-validation will be used to evaluate the model performance with different hyperparameters. This divides the dataset into 5 parts, trains the model 5 times, and uses different parts for testing. Grid underscore search dot fit uppercase X, lowercase y. This fits the model to the data, performing the grid search over the hyperparameters. It will try all combinations of the specified hyperparameters and find the best one. Printing the results. Grid underscore search dot best underscore. This gives the combination of hyperparameters n underscore estimators and max underscore that resulted in the best model performance. Grid underscore search best underscore. This gives the best score achieved during the grid search using cross-validation. What happens during grid search? Cross-validation, the dataset is split into 5 subsets, since CV equals 5, and for each combination of hyperparameters, the model is trained 5 times, 1 for each fold, and evaluated. Hyperparameter combinations. It tests all combinations of n underscore estimators and max underscore depth in the param underscore grid. In this case, there are 2 values for n underscore estimators, 100, 200, and 2 values for max underscore depth, 10, 20, so it will evaluate 4 combinations in total. Best parameters and score. It selects the combination of parameters that provides the best cross-validation score and outputs them. This means that using 200 trees, n underscore estimators equals 200, and a maximum depth of 20 for each tree resulted in the best performance on this dataset, with a cross-validation score of approximately 96.67%. You've just tuned your first model using grid search. Summary. Model selection is all about choosing the right algorithm based on the dataset and task. Hyperparameter tuning helps optimize model performance, and cross-validation ensures generalization. We used grid search to fine-tune our random forest model. Next week, we'll dive into big data in the cloud and explore how cloud platforms handle massive datasets. Stay tuned for week 9 on Let's Talk About Data.